Okay, thanks. So we were talking last night about what to say, and Seth pointed out, well, no one really knows what quantum computers will ever be used for. And I said, well, okay, but wait a minute. I mean, we know far, far more about this than we know about almost any of the other questions that will be discussed at this conference. So maybe, it would be good if I start by just, presenting like something about what we've learned from the last 25 or 30 years of quantum algorithms research. And by the way, we know a lot more about what quantum computers could ultimately be used for than we know about what they could be used for within the next few years, ironically enough. Because for the former question, is it a question of pure theory, really? And the applications of a quantum computer that have been discovered to date are more specialized than many people would like them to be. They're certainly more specialized than popular articles would give you the impression that they are. Okay, but to me, what's miraculous is that there are sort of any interesting applications at all for this really bizarre hammer of interference of amplitudes that nature makes available to you. So I would say that there are really 5 main classes of applications that have emerged over the last few decades. The first one is simulating quantum physics and chemistry themselves. That was Feynman's original application when he proposed this idea around 1981. In some sense, it's still the best application. It's what a quantum computer, in my opinion, it's what a quantum computer would do in its sleep. But it's actually useful for material science, maybe designing high-temperature superconductors, better batteries, solar cells, chemical reactions like the one that makes fertilizer. At least, given a candidate, you could simulate it and have this facility that that would let you see what's going on. And we're much more confident there than we are with many of the other applications that a quantum computer will actually be giving you a speed up. The second is breaking cryptography. That's the famous application that put quantum computing on everyone's radar with the discovery of Shor's algorithm 25 years ago. So we know polynomial time quantum algorithms for factoring, discrete logarithms, elliptic curve problems, a few other problems in number theory and group theory, which together break almost all of the public key crypto systems that are currently used to secure the internet. And these are problems where the best-known classical algorithms take exponential time. I should stress that these speedups are for extremely special problems, so not NP-complete problems, just the ones that we happen to base crypto on. Okay, but even within crypto, there are candidates for quantum-resistant public key crypto systems. That in a world with quantum computers, we could switch to those systems. Now, number 3 would be combinatorial search and optimization problems. So there's another important quantum algorithm called Grover's algorithm that can solve almost any search problem in about the square root of the number of steps that would be needed classically. So it's not an exponential speed up like Shor's algorithm, but on the other hand, it has a much, much broader range of application. Unfortunately, we also know that in the sort of generic case, that square root speed up from Grover's algorithm is the best that even a quantum computer could give you. Okay, which means if you want like an exponential speed up for a combinatorial problem, you have to exploit structure somehow. There are candidate algorithms that try to do that, like the adiabatic algorithm, something called QAOA. Okay, but even after years of study, we still don't really know if these algorithms will give a win for any instances that matter in practice. We might have to try it out on a real quantum computer before we know. Fourthly, machine learning. There's been huge excitement about quantum machine learning in the last decade. A lot of it originated with an algorithm that Seth was a co-discoverer of in 2007 called the HHL algorithm. Unfortunately, experience has shown that it's really challenging to find real-world cases where these quantum machine learning algorithms work, and there were not comparably fast classical algorithms that do the same thing. Until a year ago, one of the best candidates we had was for recommendation systems, like recommending movies in Netflix. Unfortunately, that algorithm has now been dequantized, actually by Ewin Tang, who was an undergrad who was working with me. I think the challenge remains open to find an exponential speedup for machine learning that's going to matter in real life. We don't know if there is one. And then fifth, there's a very recent class of applications that involve not using a quantum computer to do a classically infeasible calculation as much as using it as a prover in some interactive protocol to prove something that a classical computer would not have been able to. So I proposed a protocol a year ago for a quantum computer to generate random bits, by itself not impressive, but then prove to a skeptic that the bits really are random so that they could be used in proof-of-stake cryptocurrencies, for example. I expect that there will be a lot of other applications to be found in that sort of space of the quantum computer using its quantumness to prove something about what it's doing. So surely there will be more applications that no one has thought of yet, but if they seem more limited than you might like, well, part of the problem is coming up with enough candidate problems, and part of the problem is that we don't know the limits of what classical computers can do. And a secret of this research is that sometimes it's much easier to come up with the quantum algorithm than it is to rule out that there's a classical algorithm that could tell you the same thing.
Thank you. We go now to Michele.
So I also agree that some of the most exciting applications would be simulating, sort of knowing more about strongly coupled quantum many-body systems with an eye towards gravity. This is one of these very exciting potential uses. We're starting to know more and more about this, not to sort of exhaust the duality arguments, and people roll their eyes and we were tired of talking about this. But really there's been some exciting ideas, results from Dan Harlow and Garnet Chan around fully commuting Hamiltonians, and that could potentially reduce the resources down. Now the resources are still a massive problem, but in terms of why do we want to do this, this is a strong motivator. So there were some results from Sachdev in Boston, I think, and he's looking at sort of this dictionary correspondence on, and again, the physics of 80 Kelvin is pretty questionable when we're talking about this kind of thing. But there's in a case where conformal field theory doesn't have a simple quantum gravity dual, but then we sort of say let's modify it and go to a large n limit, and it does have a gravity dual. What if you had a quantum computer? This would the sort of problems with the physics on that level that they're looking at are not as, they're no longer the same. So that's one thing. I think it would be very useful. Everybody's talking about sort of NISQ. There's a lot of marketing around this, but it would be very exciting to see if we can sort of pull out a one-dimensional problem that sort of a small 1D problem that a quantum computer can calculate. Okay. Near term, noisy intermediate scalable quantum algorithms. So there's a search for this sort of quantum supremacy regime within a lot of corporates and within startups. And the idea there is, in my opinion, I'm a little bit concerned about this because I feel like that's not really good enough. Sort of counting the qubits. It's one thing to sort of onboard academic research programs, but you really need a sort of a systems view to get to an architecture that's going to do some of these things that we're so excited about, in the first place. So, for example, Google now has this sort of 72 qubit physical qubit bristle cone architecture that they say costs $100K per chip. So, okay, I'm willing to take them on their word that it's $100K. What does it actually mean? You really have to take into account sort of the classical peripheral overhead of the system. So, for that 100K chip, you have maybe a dilution refrigerator that's 500K. We know it's more than that, but I'll just be generous here. You have these sort of amplifiers, attenuators, nitrobium coax cables that need to go across fridges to manage the signals in and out. And let's say that's 400K. So all in, it's a million for this 72 qubit chip. That's 14,000 per qubit. If you are actually engaging with the numbers that would be needed to scale a quantum algorithm and for a cloud, we're talking about on the order of 10 to the 6th qubits. So the LHC did not cost 140 billion, and there's some question as to the cost benefit around that. But so I think the two main points that I'm concerned about are the lack of focus on logical computation, and what I now started calling digital error correction for quantum computers, because I think that I started calling it this to distinguish it from the control level hardware error correction that people do, which is sort of this one-shot measurement readout kind of thing, and people ask your favorite experimentalists and they will say that they have this sort of error correction, right? But really what's needed is a much more complicated, in-depth, higher level engagement on the fact that these machines are not standalone devices, and we have error rates. They're basically error correction machines, right? So you need to be optimizing and programming and managing the classical data that's coming out of these machines.
Okay, so I guess when we posed this question last night, one of our initial reactions is how to generate actual controversial statements with a question like this. Since if we went through just the basic applications of quantum computing, I think we all agree here. And Scott, for example, has done an excellent job introducing all the basic applications that pretty much I think everyone in the panel is in agreement. So I thought I would extend this to say things that are a little more controversial in the spirit of the FQXi. So I'd like to think about this question more in the far distant future. So in the sense of will quantum computers ever be useful, focusing on the ever part of if we had quantum computers and if we were able to overcome the monetary and resource constraints in the far distant future, what sort of other interesting applications can we have? And of course, we have a lot of the well-known computational problems, but I would like to focus on some potential interesting questions we may be able to answer on the more foundational side. I think one of the key questions that from the quantum foundations community is, of course, the measurement problem. That when we have observer, whatever it means for something to be conscious or something to be observer, the action of observer observing auxiliary system collapses the wave function. And in a certain instance, we would interpret this as a raise in entropy in the sense that this process is irreversible. Whereas in other instances, if we look at the phenomena of Wigner's friend, one of the postulates is that the measurement can be reversed. And I think this is one of those deep philosophical questions that we cannot answer with near-term technologies. But as we gain progressively better and better control of large-scale quantum systems, we can begin tackling this. So over at breakfast today, I was actually talking to Eric Cavalcanti, who recently had this very nice paper about building a stronger than Bell inequality constraints for looking at exactly looking at this Wigner's friend scenario to ask whether or not a wave function actually collapses or whether we can sort of reverse this collapse in the future. And to answer this question, of course, we can simulate the predictions of quantum mechanics using systems of 1, 2, and 3 qubits. But this is not very convincing, since if we believe the laws of quantum mechanics hold for 3 qubits, then we're going to get, our experiments is going to align with the predictions of quantum theory. And the interesting thing comes, of course, once the measurement system we control becomes progressively more and more macroscopic, to progressively more and more simulate that of an actual practical observational system. So we can think about, as we gain better and better control in quantum computers, to better and better model what we expect an intelligent agent or intelligent conscious system to have. Obviously, there is no fine line of where we would say something is intelligent. There's no fine line of where we would classify something between sort of an inanimate object and something that has consciousness. But we have properties that we may expect a conscious system to have. For example, the ability to learn or the ability to adapt. And if we could begin to build progressively more and more sophisticated quantum networks that can imprint a lot of these behaviors that we expect an intelligent agent to have, then we may be able to build a simulacrum of a conscious thing and observe if at any stage sort of the collapse of the wave function actually occurs using these testable inequalities that's akin to Bell inequalities, but rather to measure measurement collapse. And I think this is one of the most exciting things to me as a physicist for what having universal large-scale quantum computers can do. And of course, this is by far something that will not happen in the next 5 or 10 years. This requires us to be able to build essentially macroscopic quantum systems to the level that we're able to reverse every interaction inside them. And this is something that perhaps something that quantum computers will, in the far distant future, be useful for. But it's something that I find personally exciting. The one other thing I want to mention is, if we go back to the more pedestrian thing, I think the one last thing I want to mention that I don't think has been discussed so far is that we know that the classical amount of information that's required to track a quantum system, even if it's just to track a sequence of stochastic observations, can grow unbounded, despite the fact that the physical system itself is bounded. So Howard Wiseman, for example, has done a number of papers looking at the amount of classical information needed to track the observations of an open system. So this tells us that certain stochastic processes, to sample them efficiently, may require an unbounded amount of classical memory. So if we can find interesting processes to sample that people out there actually care about, then that could also be a near-term application of quantum computing. I'll leave it there for Seth to talk about some more adventurous stuff, or sing.
I'm going to talk about something much less adventurous. I think Scott did a great job of summarizing what quantum computers might be good for. Let's just say where we are, which is an extremely exciting time for quantum computing. If you look at the devices made by Google, IBM, or ion-trap devices made by IonQ, they have between 50 and 100 qubits, and their current coherence rates for multiple operations is something like a factor in error rate of 1 in 200 to 1 in 500. And if you could actually extend that, so it's an error rate of 1 in 1,000 to 1 in 10,000, which is a difficult but by no means impossible quantum mechanical engineering problem, which we hope will make a lot of progress on the next couple of years, then these applications like quantum simulation will be, we can do them pretty much right away. In fact, already in quantum simulation, if you build special purpose quantum devices that have tunable Hamiltonians, right now you can use them with 20 to 50 qubits to investigate things like many-body localization, which are very important things in solid state. In fact, what everyone thinks of the D-Wave device for whether it solves hard combinatorial problems or not, is a very beautiful tunable transverse Ising model, which is a very hard problem to simulate. So that's great. Possible applications include quantum machine learning. I will actually talk about that in the future, so I won't talk about it anymore now. And then there's Shor's algorithm, which is the killer app for quantum computers, but it also happens to be in some sense the suicide app, because if tomorrow we build a scalable quantum computer, which would factor large numbers and break all these public key cryptosystems, then all you have to do is demonstrate it once, and nobody would use those public key cryptosystems any longer. Really, the only way to make money from it would be to keep it secret and sell your services to the NSA and to international criminal organizations. So anyway, that's as you mentioned, that Michele mentioned, the technological problems in making a scalable quantum computer, where say with 1 million qubits and able to do 10 million or 1 billion operations, that's very daunting. You might need, with current technologies, your superconducting chips would have to be the size of this table. That's hard to do. So I would say that the projection for that is somewhere in between 15 years plus or minus never for building these things. Anyway, our esteemed moderator asked us to sing a song together, and there was reluctance on the part of my co-panelists to do this, so I decided to take the bull by the horns, and I volunteered to do this. So with apologies to Gilbert and Sullivan, I will now sing you a song that to me Well, it's a sad song, but it states the kind of where things are with quantum computing right now. In a superconducting circuit, a little qubit sang entangled, entangled, unentangled. And I said to it, qubit, oh, why do you sit singing tangle, entangled, unentangled, unentangled? Is it just decoherence, qubit, I cried, or a nasty quasi-particle in your little inside? With a shake of its poor little head, it replied, entangled, entangled, unentangled. Its flux fluctuated as it sat on that chip. Oh, entangled, entangled, unentangled. Its Josephs and junctions were having a pip. Entangled, entangled, unentangled. It sighed and it sobbed, and a quantum jump it made as it lost all the phase of its de Broglie wave. And a spin echo arose from the suicide's grave. Entangled, unentangled, entangled. That was a spin echo joke, by the way. Now I feel just as sure that I'm sure that my name isn't entangled, entangled, unentangled, that it was not spontaneous collapse of the wave function that made it exclaim, entangled, entangled, unentangled. If my neurons interact with the universe, I shall decohere as it did, and you will know why. But I probably shall not exclaim as my coherence dies. Entangled, entangled, unentangled.
Thank you very much. So actually, I was launching this idea, and thank you, Seth, for taking it.
The most important thing I forgot to say before is that for me, I talked about 5 different applications. Maybe, you heard from the other panelists about some others. For me, none of those are the main application. The main application of a quantum computer is to disprove these people who keep coming to my blog and saying, well, quantum computing will never work. I thought about it for 30 seconds, and here's, an obstacle that no one in this field, that must never have occurred to you, right? That it's basically just an analog computer, right? Or, like they've never heard of error correction or anything, or what makes you think this quantum mechanics is true anyway, right? It's just something some physicists made up. And I would like to sort of rub these people's faces in the reality of the exponential wave function. And for me, everything else is icing on that cake.
I feel like we're all, there's one FQXi where somebody said we're all Alan Guth. So I feel like actually my answers were sort of distributed over this table, and so there's not too much to say. But I agree that for these two other reasons, those are my top 3, and I hope there are no investors in the room, but that's definitely the most exciting aspect to me. And yeah, I kind of call what you were talking about like Deutsch's parable, right? So like, can you run an AI and sort of check? It's also Wigner's friend, right? So yeah, these are cool ideas.
So I guess the one last comment I thought is quite interesting. It may not be exactly what quantum computers are useful for, but I think an interesting implication is there's exponential increase in capability depending on the size of the computer, which I think is one of the things that is quite unique among other physical resources. So usually when we think about classical computers or any other resource, when 2 countries combine their resources together, the capabilities that they do is generally scales linearly with the combination of resources. And this certainly applies with physical resources and to extent classical computers as well. And one of the interesting things about quantum computers is that when we add a fixed number of qubits to a quantum computer, it seems like for certain problems, and certainly for the ability for us to classically simulate it, the complexity seems to grow exponentially. And this has some interesting sort of social political implications, and this is something that Peter Rodi, I believe, has spoken quite a few times about, is that you can have instances where there's a strong incentive for countries and other entities to collaborate with each other, assuming that we had a coherent method of transferring quantum information. And I think this in itself it can have dramatic ramifications in what quantum computing devices, how people use them, as it creates a strong incentive for entities to work together to do something greater than what they can do themselves, even if it's just collaborating with an entity with relatively few qubits or relatively small amount of resources. Even a modest contribution can greatly improve the class of problems that we can tackle. And I think that's an interesting property of quantum computers to point out.
So I'd actually like to say something about quantum information theory as opposed to building quantum computers. Now, note that what was Turing's amazing contribution? He took Gödel's undecidability theorem, he showed this applies to a computational device. So he made the model of a Turing machine, of a machine that does computation in order to talk about what is computable and what is not computable. Now, the world is quantum mechanical, and our devices and our computers are at bottom quantum mechanical. So if we want to know how information can be processed in the universe as a whole, we have to look at quantum information processing. We have no choice. And it's a bonus that we can actually build these devices, and we're in the middle of a very exciting time of building more powerful quantum computers, whether large scalable quantum computers will ever be built. But let me just say something in favor of quantum information theory, which is a theory that kind of came out of foundations of quantum mechanics during the 1980s, prior to quantum computers being, prior to people even thinking you might build a quantum computer. Look, quantum information theory is a universal language for discrete quantum mechanics. And it tells you how entanglement works, it tells you how you can compute things, it tells you how communication works. Quantum communication, by the way, limits the communication capacity of fiber optic cables, which are actually quite close to their quantum capacities. And it's now gotten to the point where, my God, even people who do ADS CFT theory and string theorists are now doing quantum information. There goes the neighborhood, I say. And that's exactly because, quantum information theory tells you when you have discrete quantum systems how they can behave. So as a way of understanding the way the universe works, I'd say that's the most important application of quantum information theory. We can't actually understand the way the universe works unless we see how it processes quantum information.
Francesca Vidotto from Western Ontario. Just a short comment, since you were mentioning DSCFT. To me, the most interesting reason, the reason why I want quantum computing to work is because it makes a fantastic quantum simulator for the loopy quantum space-time. So there are already ongoing work to do this in partnership with IBM and with also people in Waterloo.
Yeah, let me comment on that. The reason, so the history of applying quantum information to ADS-C comes from Brian Swingle, who, when he was a graduate student at MIT, noted that there's a connection between quantum error correcting codes, which allow you to store quantum information in a distributed fashion in a system, so that you can recreate it over here from these bits over here, and you can also recreate it from these bits over here, and that gives you insight to how you could have the same quantum information in the bulk and on the boundary of anti-de Sitter space. So it's a remarkable insight. I don't mean to diss it, I think it's completely cool.
So my question to you is, do you know of any of the often talked about interpretations of quantum mechanics today that have stuck their neck out and said that if you can build a really large quantum computer that seems to obey the Schrödinger equation, they will consider their interpretation ruled out?
Max, the thing that you're asking for would not be an interpretation. It would be a rival physical theory. It would be making a prediction that's different from the prediction of quantum mechanics. There are quantum computing skeptics who think it can never be built, right? Either because they don't believe quantum mechanics, or they just believe that there will be, some noise, some principle on top of quantum mechanics that will sort of censor quantum computation or prevent it from ever scaling. that itself, if that existed, I think would be a revolution in physics.
Yes.
And that's not, so that's not attached to any interpretation like, Copenhagen, Bohm, many worlds, and, to the extent that any of them, made sense to you before, I think they still make the same sense to you in a world with quantum computers because they all predict exactly the same thing about their functioning. GRW, I would precisely regard as a rival theory. But by the way, a super cool observation is that even if GRW was true and there were like real spontaneous collapses, you might be able to treat those as just another source of noise to be dealt with by quantum error correction and just go right on building your quantum computer.
May I actually say that to the extent that GRW has been falsified, right, so that it's limited the spontaneous wave function collapse to a very small level, and those are already things that you could deal with quantum error correction, because the actual noise that people are looking at, which is an error in one part in 10 to the fourth or 10 to the fifth, is much, much larger than you'd get from GRW. So then to have GRW prevent quantum computing from happening, it would have to be different.
Up to some scale. Actually, I'm working on that, trying to falsify on GRW. Okay.
Regarding the sort of Brian Swingle stuff and the error correcting codes, I mean, it would be nice to sort of, that there's a naturalness argument there, right? That okay, we live in a quantum universe, and these are topological qubits, and we need a lot less error correction, and it would make all of the work that we do on error correction completely irrelevant. And so it's not like this sort of forcing mechanism of let's just force the noise out in this little fraction of a Hilbert space. So that would be cool if Microsoft should stop slacking.
What is the most destructive, counterproductive, and destabilizing outcome of developing quantum technologies that you could imagine might happen?
Well, quantum computers are not very dangerous right now. The worst thing that can happen is if you drop one on your foot. So, yeah, and of course, as you're suggesting, the primary application of quantum computers right now is to put them in your funding application to get money, which is a very near-term application for quantum computing.
I think in some sense it's a sociological thing. So it's almost like the U.S. government has decided we're not going to pick winners. The UK has decided we don't want to hurt anyone's feelings, and we're going to sort of fund everybody. And China is just massively doubling down on all budgets and having the government build the qubits, whereby the startups get to sort of capture, the startups get to work on some of the problems that are really, really important to get these machines to run, get to capture the value of subsidized qubits. So what's going to happen in terms of being able to collaborate? I think that's something that could become somewhat even tragic if things go classified in a way that...
Can I ask you if this is what you had in mind when you asked the question?
Yeah. Maybe I misunderstood the question. I thought Matt was asking for the most destructive application that he could imagine.
Yes.
I mean, the obvious thing to say about that would be, the use of Shor's algorithm to break public key cryptography, and you could imagine all sorts of things falling out from that, like maybe someone would decrypt some emails that would, sway the outcome of a presidential election, or, lead to some clowns being elected. I mean, obviously that could only happen in a world with quantum computers. But I mean, there's all sorts of mayhem that could ensue.
Yeah, I think everyone has pretty much summed up my views. I can't see anything particularly destructive about quantum computers at the moment, other than perhaps decrypting some sensitive messages in secret when Seth sells his quantum computer to the black market.
Which is happening anyway.
Which is happening right now, I presume. But other than that, well, obviously our knowledge of the applications of quantum computers is fairly limited at the moment. And just like I think classical computers in the 1960s, where we could only think about decryption as their major use, and now we use them to watch videos of cats. From the perspective of quantum computers, I think it's a very similar regime. We are currently at the level where we don't have a functioning quantum computer to the sophistication that we'd like, so we don't really know its applications. But I don't believe that there is any particular application that would be catastrophically destructive in the sense of being able to, because I can't see solving a problem as being catastrophically destructive, at least from my naive point of view at the moment.
I'm curious, this is maybe just a silly question, but could a quantum computer at some point in time be used to prevent decoherence in an external system? So I have something in my lab that I don't want to decohere. I plug in my error-correcting quantum computer and I prevent the decoherence in that external system. Is that a possible thing that could be done?
I mean, at that point, the other system that you've prevented from decohering, I would tend to think of it as just itself a quantum computer, right? I mean, it's been said, like if you actually wanted to build a Schrodinger's cat in reality and, have it remain in the alive plus dead without decohering, your best bet is probably to build a simulated cat that is inside of a fault-tolerant quantum computer, right? But you could extend that reasoning to all kinds of things, and yeah.
And there are recent protocols, I think by Magona-Vasquez, that looks at sort of restoring certain open system open quantum systems by continuous measurement. They happen with a probabilistic success rate, but I think that's what you would do short of putting a virtual cat in your quantum simulator, which is probably your most stable solution.
Hi. So as Scott touched on, one of the problems with demonstrating quantum advantage is not actually finding the quantum algorithm, but finding what the best classical algorithm is. And so often, as he said, it's just that you find a quantum one that's better than the existing classical. And this has led to this sort of dequantizing of algorithms. So let's suppose that practical, useful quantum computers aren't built in the next several decades and the field dies. But in the process, we're left with several dequantized classical algorithms that beat the presently known algorithms. Would you then class quantum computing to have been useful, even if we don't have a quantum computer, just because it improved classical algorithms?
So the question was, if quantum computing merely leads to sort of spin-offs for classical computation, is it a success? I would say, depending on how good the spin-offs are, sure. I'll take that. I mean, no, there already have been really exciting spin-offs for classical computer science that have come out of quantum computation. With new algorithms and also new impossibility results. Because this has just put this new and unusual set of demands on theoretical computer science, and so great stuff has come out of that. I hope that will continue to happen. But it's kind of like string theory, right? Where is string theory a success if all that comes out of it is new insights for condensed matter physics or quantum field theory? Right. Well, depends how good they are, I guess.
When Charles Babbage was funded by the British Admiralty to build the difference engine in the 1830s, it was a Manhattan project size scale of funding, and it failed. And the reason it failed was because he discovered in trying to build it that the machining techniques were insufficiently precise to machine the gears of the difference engine so that they could actually turn and could overcome friction. And so they spent, the equivalent of $1 billion or more trying to build this device, and it failed. But the results were that they didn't get a mechanical computer, but they were able to machine gears to 10 times the tolerance as before, and this had a tremendous effect on the Industrial Revolution. So this was told to me by one of my colleagues in mechanical engineering. So that in of itself would be great. And of course, you already see, remember that for the last 20 years now, or 15 years, the world's most precise measurement instrument has been Dave Wineland's quantum logic optical frequency atomic clock, which operates by exchanging entanglement between hyperfine levels and optical levels of atoms and explicitly uses quantum information. So this has already happened with quantum information and is likely to continue to happen.
One remark on that. I mean, I think it would be fantastic to have better multiplexers and single photon sources, and a lot of that is what this in part I think is about. It's a little bit like at the moment having Abaci, but if you really want to have a sort of a quantum computer, you need to put forth sort of conditions on architectural designs and have many people talking about that in terms of footprint and although size cost may sound like a hollow argument, there's an implicit kind of request there for miniaturization and densities to get to something that could do quantum simulations to get to logical qubits in the first place. So I think there needs to be a focus on that if we're going to see these kind of more sci-fi applications like what we've been talking about.
Great. So let's thank Catalina and her
And
awesome
thank to all
panel
the panelists.